This is Physics 2120, Lecture 23, and today we're going to continue to talk about electromagnetic waves. So last time we talked about how electromagnetic waves can transport energy. They can also transport momentum. So this momentum is absorbed by a surface, and therefore a pressure is exerted on the surface. So if we're assuming a wave transports, say, a total energy U to a surface in a time interval delta t, the total momentum is U over c for complete absorption. The pressure then is defined as force per unit area. So force over area, that's the same as 1 over area times the time rate of change in momentum, which is 1 over c times the time rate of change in energy, how fast energy is being delivered, divided by the area. We also know, though, that the magnitude of the pointing vector is du dt over a, so the pressure is the pointing vector over c. That's true for a perfectly absorbing surface. For a perfectly reflecting surface, we're going to have twice the change in momentum, and therefore twice the pressure. And for a surface with a reflectivity somewhere between a perfect reflector or perfect observer, the momentum delivered is going to be somewhere then between U over c or 2U over c. For direct sunlight, the radiation pressure of sunlight on a surface here on the Earth is about 5 times 10 to the minus 6 newtons per square meter. We can determine radiation pressure by an apparatus as shown here in the figure. I shine light on this surface, and let's say that these two, a black disc and a mirror, are balanced and they're hung in a vacuum. That's what this glass is around, right? Pump a vacuum. It's hung by a single thread. Then as light comes in and shines on the black disc and the mirror, and the black disc absorbs the light and the mirror reflects the light, so the pressure is going to be twice as high on the mirror as it is on the black disc. And knowing the area of the discs, we can determine the angle through which this connecting rod rotates, and we can determine the radiation pressure. So for example, if we look at the space station, we notice that there's solar panels on both sides, and they're matched evenly in color and reflectivity. If there was more solar panels on one side than the other, there would be a net torque that might cause a rotation of the space station. So let's look at an example problem. The sun delivers about 1,000 watts per square meter of energy to the Earth's surface via electromagnetic radiation. Let's calculate the total power that's incident on a roof that's 8 meters by 20 meters. Let's determine the radiation pressure and radiation force on the roof if the roof was a perfect absorber, say it's a black roof. So first, we can use the pointing vector, which is the average power per area, to figure out the average power. So that's S times A is 1,000 watts per square meter, and the roof is 8 meters by 20 meters, and we get 1.6 times 10 to the 5th watts. That's a lot of power. Right, that's 160 times 10 to the 3rd, or 1,600 100-watt light bulbs could be lit just from the energy incident on your roof. So the average pressure, we said, is S over C. So 10 to the 3rd over 3 times 10 to the 8th, so it's 3.3 times 10 to the minus 6 pascals. Or to figure out force, force is pressure times area, so we multiply again by the area, and the force on the roof is 5.33 times 10 to the minus 4 newtons. So the force is pretty small, but it is not zero. So how are electromagnetic waves produced? More importantly, we might be interested in sending or receiving electromagnetic waves as a signal. So stationary charges or steady currents cannot produce electromagnetic waves. The fundamental mechanism responsible for radiation is acceleration of charged particles. Whenever a charged particle accelerates, it must radiate energy. This, by the way, is one of the reasons that quantum physics started to be looked into in the early 1900s, is if we really believe the Bohr model of an atom, of a single electron circling a positively charged nucleus, if the electron is moving in a circle around the atom, then it has to be constantly accelerated, and it would have to be constantly radiating energy, and eventually it would give up all of its energy and fall into the nucleus. We know that doesn't happen. Therefore, there had to have been something different, and we'll get to that next semester in modern physics. So, to produce electromagnetic waves by an antenna, there's many different antenna designs. The one here on the side is called a half-wave antenna. And two conducting rods are connected to a source of alternating voltage. The length of each rod is a quarter of the wavelength of the radiation that we want to emit. The oscillator forces the charges to accelerate between the two rods. So, the antenna can be approximated as an oscillating electric dipole. The magnetic field lines from the current moving up in one half of the segment form concentric circles around the antenna and are perpendicular to the electric field lines from the antenna at all points. So E and B are 90 degrees out of phase at all times. That dipole energy dies out quickly as you move away from the antenna. The source of the radiation found far from the antenna is the continuous induction of an electric field by time-varying magnetic field, and the induction of a magnetic field by time-varying electric field. The electric and magnetic field produced in this manner are in phase with each other and vary as 1 over r, and the result is an outward flow of energy at all times. Now, one of the things about antennas is the amount of energy coming off it is angular dependent. And one of the reasons we like a dipole antenna is because it forms an intensity pattern that varies as sine squared theta over r squared. So it goes down as 1 over r squared, but also if I look, most of the energy is going off sideways, not a lot of energy going up and down. So if I'm a radio station and I want to broadcast, I don't want all of my power going out into space, nor do I want all my power going into the ground. I want it to go out to the sides where it will cover lots of people and be able to hear my radio station and be able to sell advertising and make money. So we have to be careful when we design antennas that we design it so that the radiation or the electromagnetic waves come off in directions that we're interested in. So let's look at a problem, a half-wave antenna. And it works on the principle that the optimum length of the antenna is half the wavelength of the radiation being received or transmitted. What's the optimum length of a car antenna when it receives a signal of 94.7 megahertz? So, first of all, a car antenna. If you look at your car antenna, you only see part of the antenna sticking out. And what happens is it's usually on a piece of metal, and the metal forms a reflection, and we'll talk about that in optics later, so that it appears to be a second half of the antenna. So in this case, we know C is equal to lambda F. So if we wanted to figure out the wavelength, we can use the frequency and the speed of light to figure out wavelength. So lambda is equal to C over F. We do the calculations and we get that the wavelength is 3.16 meters. The length of our antenna then is half the wavelength. So we divide by 2 and we get 1.58 meters. The last thing we want to talk about is the spectrum of electromagnetic waves. So we have lots of different types of waves that make up the EM spectrum. There's no sharp division between one kind of electromagnetic wave and the next. All forms of the various types of radiation are produced by the same phenomena, accelerating charges. So if I look at electromagnetic waves, the visible light is a very small part of the electromagnetic spectrum. So we start out down here at the very long wavelengths, and of course long wavelengths means very short frequencies. So long wavelengths, radio waves, and then we get to AM radio waves, and TV and FM, and at the top of the TV and FM range is really what we use for digital TV right now. And then after that we get microwaves, and then microwaves are followed by infrared as we're getting shorter wavelength and longer frequencies. Then this very visible band between 400 nanometers and 700 nanometers of visible light. Above that we have the ultraviolet, we have X-rays, gamma rays, which pretty much go forever, the real high energy ones, which are high frequency, very small wavelengths, we even call cosmic rays. So, radio waves have wavelengths more than 10 to the 4th meters to about 1/10 of a meter. We use those in radio, television, communication systems. Microwaves go from about 0.3 meters to 10 to the minus 4 meters. They're used a lot in radar systems. Microwave ovens are an example where I can use a very specific wavelength to excite the atoms in a water molecule, the electrons in a water molecule. Of course, microwaves can also be used for communication. Microwave towers are long different distance communication between cell towers, for example. Infrared waves, wavelengths of about 10 to the minus 3 meters to 7 times 10 to the minus 7th meters. Sometimes they're called heat waves, but that's not, it's kind of a misnomer. They are produced by hot objects and hot molecules, and they're readily absorbed by most materials. The heat coming off, or the light coming off of a hot object, you can tell the difference in temperatures by looking at the infrared wavelengths. Visible light is just called that because that's where our human eye is designed to see electromagnetic wavelengths from 4 times 10 to the minus 7 meters to 7 times 10 to the minus 7 meters. And our eyes are most sensitive right in the yellow-green at 5.5 times 10 to the minus 7 meters. So, when we talk about visible light, different wavelengths correspond to different colors. So red is right around 700 nanometers, and violet, just to where you can't start to see it anymore, is around 400 nanometers. Now, where you can't see it anymore, where the top of this visible is different for different people. Some people are actually able to see a lot more into the violet and the ultraviolet range than others. Of course, ultraviolet light then would go from visible light up to about 6 times 10 to the minus 10 meters. The sun gives off a lot of UV light, which is absorbed in our atmosphere by ozone, which is good. That way we all don't cook up to crispy critters and get burned every time we walk outside. X-rays are wavelengths from about 10 to the minus 8 to 10 to the minus 12 meters. The most common source of an X-ray is the acceleration of high-energy electrons striking a metal target. For example, if I wanted to create X-rays in the dentist's office, I have maybe a piece of tungsten here, and I shoot electrons down at it. And as I shoot electrons down and they strike here, X-rays come off in different directions. And finally we get gamma rays, which are wavelengths from 10 to the minus 10 up to 10 to the minus 14 and higher. And those are things that may be emitted by radioactive nuclei as they break apart. Gamma rays are very highly penetrating, they carry a lot of energy, and they can do serious damage when absorbed by living tissue. And if I look at objects in different parts of the electromagnetic spectrum, I can get different information. So for example, in astronomy, we might look at the Crab Nebula at different wavelengths. So up here we look at it in the X-ray wavelength. And then visible light, radio waves, and infrared. You see in the X-rays you can actually see the swirl of particles around this central thing that is shooting out jets on either side. Whereas if we look at it in the visible light, it's really pretty, but we can't see what's going on in the center. So different wavelengths of light give us different information. So to review what we talked about today, we talked about electromagnetic waves, that they carry momentum, and since they carry momentum and there's a change in momentum, they can exert a pressure on something. We talked briefly about antennas, and finally we talked about the electromagnetic spectrum. You should know the electromagnetic spectrum.